In this podcast, we'll be looking at different types of intermolecular forces and their significance. If you recall from bonding podcast, we had classified bonding in two main types. Intramolecular bonding, which is what we normally call as bonding, and intermolecular bonding. Intramolecular bonding were of four main types: ionic bonds, covalent bonds, metallic bonds, and covalent network bonds. Intermolecular bonding is also of five types: four types: ion dipole, hydrogen bond, dipole-dipole, and London dispersion force. So if you take a look at a molecule which has two atoms A and B joined together through a bond to make a molecule, this red bond is called an intramolecular bond, which joins the atoms together to form a molecule and makes them function as a unit. However, once the molecules are formed, there's also attraction. There may also be attraction between the molecules through what we called as intermolecular bond, or IMF. So here we write intermolecular and intramolecular as two different types of bond. However, in more cases than not, for example, in ionic, metallic, and covalent network bond, intramolecular and intermolecular bonds are one and the same. Let's take an example of sodium chloride formula unit, NaCl. So sodium ions and chloride ions attract each other through electrostatic attraction, and that is what we call an ionic bond. So if you think of sodium as an ion and chloride as an ion and sodium chloride as a formula unit, we'll call this bond as intramolecular bond, right? Or intra-ionic bond, right? Now if you think of another formula unit of sodium and chloride, an attraction between them as ionic bond, but there's also attraction between this sodium and chloride and this sodium and chloride, which is also ionic. And this you can think of as sort of intermolecular bond. So intra and intermolecular bond are one and the same in this case. However, in case of covalently bonded compounds, inter and intramolecular bonds are distinct and different from each other. Intramolecular bonds generally have a lot more energy and are stronger than intermolecular bonds, which are generally weaker. So the question is, if intermolecular bonds are weak, then why study them? What's the reason behind studying intermolecular bonding? Intermolecular bonds, even though they are weaker, they still control a lot of properties of a substance, such as their states. Are they going to be as solids, liquid, or gas? Solid will have strongest intermolecular forces, followed by liquid, followed by gases. They also determine vapor pressure of a liquid. And the stronger the intermolecular force, lower will be the vapor pressure. They have melting points, and the melting points and the boiling points of substances are also determined by the strength of intermolecular bonding as well as their solubility. Like dissolves like. In addition, surface tension and viscosity are also two properties that are determined by intermolecular bonds. So what are these intermolecular bonds and what are their strength like? In intermolecular bonds, ion dipole are the strongest, followed by hydrogen, followed by dipole-dipole, followed by London dispersion forces. However, guys, you have to keep in mind, case by case basis, sometimes LDFs might end up being stronger than a dipole-dipole attraction. if it is an atom with a large number of electrons, with a large possible distortion, the London dispersion forces will be significant. And there could be a case where LDFs are greater than dipole-dipole attraction. You would not be able to predict it, but if you are asked to justify, then you should be able to justify that. For prediction, you'll always say ion dipole stronger than hydrogen, followed by dipole-dipole, followed by London dispersion forces. Now let's look at each of these forces. Let's start by looking at ion dipole. Ion dipole attraction happens every time an ion like a sodium ion, anytime an ion like a sodium ion or chloride ion which come from salt are dissolved in water and they interact with water. Then the attraction between sodium ion and water or chloride ion and water are ion dipole attractions. Let's quickly go to a website and let's look at dissolving of sodium chloride in water. This is the website. Let's go to the units pages here and let's scroll down to intermolecular forces. And that is chapter 11 right here. And this one here, sodium chloride in water. So this is an example of ion dipole interaction. So this is a salt crystal. And if you were to take a guess, can you tell me which one will be chloride ion, which one will be sodium? Yes, you're right. The green will be chloride ion and purple will be sodium ion because of the smaller size. A cation has a smaller size as compared to an anion because of lesser electron-electron repulsion, smaller size of electron cloud. That's why smaller is the sodium ion. Now you see a bunch of polar water molecules around it. And if a chloride ion is to be removed, then you notice how the hydrogen or the positive end of the water molecules orient themselves to attract the negative ion, and the attraction between this positive hydrogen end of the water molecule and the negative chloride ion is called as ion dipole attraction. Similarly, when a sodium ion is pulled apart, now the negative end of the water molecules attract the sodium ions and the hydrogen end faces on the other side. These attractions are called ion dipole interactions. Now the second type of intramolecular forces are hydrogen bonds. Hydrogen bonds are stronger, and hydrogen bonds are identified when hydrogen is bonded intramolecularly to fluorine, to oxygen, or to nitrogen. Then the intermolecular bond that forms is called as hydrogen bond. The reason for this is NO and F are very highly electronegative, and smaller atoms, when they combine with a small positive hydrogen, it causes extreme polarization and makes a pretty strong intermolecular force of attraction. So hydrogen bond is present when hydrogen is bonded intramolecularly to NO or F. Then the intermolecular bond is called hydrogen bond. The next type of bond is dipole-dipole attraction. Dipole-dipole attraction is when you form a dipole through polar covalent bond with a positive and a negative end. And if you have another such molecule with a positive and negative end, then force of attraction between them is called dipole-dipole attraction. For example, HCl molecules attract each other through dipole-dipole interaction. And the last type of bonding is London dispersion forces, or LDFs. London dispersion forces occur when there is a distortion in the electron cloud, which results for most of the electron temporarily to move to one side of the atom, resulting in a little negative and a little positive charge, which polarizes the atom adjacent to it to a positive and negative charge, and the attraction between them is called London dispersion force. London dispersion forces are temporary and very weak, and they are present in every single atom or molecule because everything has an electron cloud. However, it is a convention that we only mention London dispersion forces when they are the only forces present. So generally we list the strongest of the intermolecular force. For example, in water molecule, when the intermolecular force is asked, we will say it is hydrogen bond, even though there are LDFs present, but hydrogen bond is the prevalent intermolecular force of attraction. So London dispersion forces increase with the number of electrons. So as the size of atom increases, number of electrons increase, so does the distortion or possibility of distortion of electron cloud, and London dispersion forces increase. Hence, down a group, London dispersion forces are stronger. London dispersion forces are important in non-polar molecule and in noble gas atoms. Now let's quickly look at an animation of all of these forces, and then that will be the end of this podcast. Let me just get rid of this ink and let me click on the link, and that is this one. And let's look at different types of intermolecular forces: dipole-dipole, London dispersion, and hydrogen bond. Now this is an example of dipole-dipole. So you see this is a polar molecule, a negative blue end and a positive red end. And you can see that the electron cloud size is bigger because more of the electrons are present on that side. And this attractive force between them is called dipole-dipole attraction. This is an example of London dispersion force. You see how the electron cloud is distorted, resulting in a positive negative charge, and that brings about a distortion in the neighboring atoms, even though this is temporary and weak force, because it's happening in so many atoms or molecules at one time that this becomes significant. This picture explains that the larger the chain, or the more branches there are, or the more atoms that are present in a molecule, greater will be the distortion and greater will be the London dispersion force. This example here shows the hydrogen bonding's impact on boiling point. You see the things that have hydrogen bonding, their boiling point so much higher. So water's boiling point should have been somewhere here as compared to other elements in its group, but it is way high there because of the hydrogen bonding. And hydrogen bonding is when hydrogen is bonded to NO or F through a covalent bond, then the intermolecular bond that happens is called hydrogen bond. And that is the end of this podcast. Thank you for listening.